Welcome everybody. So this is a tutorial of the Restart Tutorials on Telecommunications series. So we have the pleasure to have with us Professor Fabrizio Granelli from the University of Trento. The title of the tutorial today is Network Digital Twins in 6G and Future Networks. Professor Granelli has a long experience in research. He has been involved in many activities also related to journals, scientific journals, and conferences. He's been also active in education, and he was a distinguished lecturer of the IEEE ComSoc. He is for sure an expert of the topic, so we can start with the tutorial. Fabrizio, thanks for your availability, and you can start your tutorial. Thanks.
Thank you very much, Antonio. Thank you all for coming and good afternoon. So today we will speak about network digital twins and specifically since we work in communications, we will look what is the application on 6G and future networks. So first of all, let me say a few words about the advancement of mobile networks because this can help to understand also why we need further development. So here I'm presenting a few diagrams about what is happening currently. So you know we are in the period where 5G is being deployed and the community is already designing 6G. So no one knows exactly what 6G would look like, but for sure we know that some features will be extended from 5G. For example, we will have extended data rate up to 1 terabit per second, probably higher reliability, lower latency, also higher precision in localization and so on. But those are performance metrics. So what will be the architectural modules, the novelties that we expect from 6G? Well, in order to enable 5G to fully exploit the softwareization and potential automation that it brings, most likely 5G will need to bring additional functionality, especially to support automation. And we believe that AI and machine learning will have an important position and they will provide an important contribution towards the development of 6G because the automation will be one of the key features to enable highest performance and also additional flexibility. And if we look at the ITU documents that outline what they expect from the 2030 generation of mobile network, of course, 6G will represent an extension of 5G. And this diagram, I think, conveys very well the idea that if you are familiar with 5G, there is typically this triangular diagram that shows the typical 3 types of main applications that are enhanced mobile broadband, massive machine type communication, and ultra reliable and low latency communications. That here are in the middle of this diagram because 6G will sort of distort this triangular structure into an hexagonal structure because there will be 3 more important features. One will be integrated sensing and communications that you will probably get a tutorial later on in the next weeks, AI and communications, and of course, the main goal will be the Internet of Everything. So we will have the concept of ubiquitous connectivity. And to achieve this, you see one of the main features is AI in communications. Another important message from ITU is that if you look at the outer circle, there will be society goals that will more directly be targeted by 6G, like sustainability, connecting the unconnected, security and resilience, and ubiquitous intelligence. So, of course, with digital twins, we don't solve all the problems, but I will try in this presentation to solve you how we might use digital twins to address some of these challenges. So Let me, for those of you that are not familiar, introduce the concept of digital twin first, and then let's apply it to networks. So the digital twin is an emerging concept in communications, but it's also quite mature in other scenarios. And what we mean by digital twin is we need a digital copy, we mean a digital copy of what is called the physical twin, of a real object, of a real process, for example. The main features that distinguish a digital twin from a simulator or a model is that the digital twin is characterized by the three pillars that you see in this picture. So, of course, it's a virtual representation. So it accurately models the physical details of the original, but also is characterized by two other important features. One is the accurate synchronization, because the digital twin is expected to represent the real state of the physical counterpart in real time. So we should have an exact copy of an object in the exact state that it is. And this is provided by the ability or by communication link between digital and physical twin. That is the one that allows for real-time updates. So there is a continuous link between physical and digital twins that allows one to interact with the other. On one side, for example, we use this data flow to transfer the state of the physical twin to the digital representation. On the other way around, the digital twin can be modified, and its modification can impact also on the physical twin. We can discuss about that, of course, later on. So basically, when we speak about the concept, we have a physical entity that we start from, and we build a digital model of that. Plus, we provide real-time communication between the two through data connection, and we will use analytics tools in order to exploit this softwareized version of the physical entity. So some application scenarios are already quite well known. For example, in manufacturing, it's quite common today to apply the concept of digital twins, because you can have a digital version of a real system or a real process and use it, for example, for predictive maintenance, because you want to understand if it's going to break, for example. Healthcare, there is the concept of digital twins of humans also, so to replicate your health, so your personal information, in order to enable for a better patient analysis and treatment. You can use digital twins in the supply chain, for example, to enhance efficiency, or in construction, because you can monitor building performance and also, for example, aging of the buildings by sensors that you put on the real system. And then you can study ways, for example, to fix problems without directly operating on the real system. And a whole big and promising scenario is also the smart cities, because smart cities are very complex system of systems, and there the digital twin can be applied in a lot of different situations. At the end of this presentation, I will present you a few examples. So, but the possibilities, of course, are endless. So the important thing that I would like to focus today is that you can build a digital twin in several ways, and I will present you some examples in a few minutes. But the most important aspect is the connection between the physical and the digital twin. So you can have a version of a physical object that is a simulator, can be a mathematical model or another thing, but this becomes a digital twin when you connect it to the physical twin. So there should be a continuous link between the physical and the digital counterpart that allows to maintain the two objects synchronized. So you need the digital twin to be always exactly synchronized with the physical version. And this, I will show you, it's one of the biggest challenges in building a digital twin, especially in the area of communications. But before going to that, let me conceptualize a little bit the entire ecosystem. So how do you use a digital twin? And here we can use a model that is similar somehow to the TCP/IP protocol stack, but in the case of digital twins. So, you know, in the TCP/IP protocol stack, typically you can use a layering model or a hourglass model where in the middle you have IP as the glue that glues every network together. And here instead, this feature is provided by what we call a digital twin layer. So a layer that enables to generate digital twins. On the top of this, you have a digital representation layer that will explain how to represent the digital twin, how to build a digital twin. And then you will have a service layer on the top where you can provide the services. We will see later, but for example, you can use a digital twin for what-if scenarios. You can use it for training AI, or you can integrate one digital twin in another, or integrate it through interfaces in a real system. I will show you also some examples about that. Below the digital twin layer, you will have, of course, at the bottom, the physical twin. For example, it can be a 5G infrastructure, it can be an application, it can be a renewable source, a city, a person. This represents the real space. And you need this cyber-physical interaction layer that allows for the communication between the physical and the digital twin. So that is basically the whole ecosystem. So when you plan to use a digital twin, somehow you will need to have some of those features and put them in the system that you want to enhance with the digital twins. So now that we saw what is the digital twin, let's see how and why we can apply these to networks. So, you know, networks, as we saw at the beginning, they are continuously evolving. And today there are four main, let's say, directions of innovation that you can see in this picture. So networks are becoming more and more softwareized, also automated. There is this trend of integrating AI and machine learning for networking, and also the issue of sustainability. And somehow the network digital twins can help on all these scenarios, because in all of those scenarios, you can use a digital twin for analyzing scenarios, so for evaluating changes and impacts without requiring to work on the real system. So you can play with digital twins and see what happens. You can handle heterogeneity, because digital twins are a sort of a common language that you can use to build twins of different natures and combine them together. You can especially exploit predictive capabilities. So you can forecast, for example, network issues or the user demands based on the real situation. And for sure, you can use a digital twin to increase self-awareness. So you can monitor the network state at the very high level of detail and understanding in real time what is happening in the system. And this means that I see the digital twins of networks as a tool, especially for network management. So we can simulate scenarios, we can provide proactive maintenance, we can enhance performance, we can detect anomalies, make predictions, predict failures, forecast demands, help interoperability. So there are a lot of features that we can exploit by the integration of digital twins in the network management. And the first scenario is about how they can be integrated in 6G. 6G is one of the natural places where digital twins of networks can be integrated. And especially, there are several research projects today that address this issue. For example, I'm involved in this HORSE project that is from SNSJU. And here we built a very complex system, most oriented to automatically handling security in 6G. But without going into the detail, the important aspects of this system are that there is a component in this system that is the purple one in this picture, where we implement digital twins for emulating the context of operation of the network. And this allows us to predict potential security attacks, but also to analyze the impact of those potential attacks, so that if the system decides, for example, to perform an action to prevent an attack or to mitigate an attack, before executing the action, it can use the digital twin to predict what would happen, so to analyze if that action will be really positive or if it will have, for example, side effects. If you want a better way to look at this procedure is in this diagram that shows you that typically you can have the traditional, let's say, machine learning for attack detection on the top, and this module that is called DEME performs machine learning for threat detection. In this case, it's sort of in real time. You can analyze for potential threats. If you detect an attack, you will trigger the corresponding mitigation action. If you introduce the digital twins, you go in the solution that is in the bottom, where on one side you can use the digital twin, that here is the SAN, the sandbox, that can predict attacks, because the digital twin can look in the future and say, maybe there is an attack coming in, so it can prevent even the attack, and it allows the system also to decide for a preventive action to be performed, but before implementing the action, it can use again the digital twin in order to perform what is called the impact analysis. So I can check the outcome of a potential action for mitigating an attack before requiring to implement it, so that at the end, I will apply only the action that the digital twin predicted as the most effective. Here there is a sort of more detail, but the concept is that through the digital twin, you have access to a lot of information, but organized in a way that is in the form of a simulator, an emulator, or even a model that is simple to interact with, and it allows to perform predictions, what-if scenarios, and analysis of the results. Just to give you an example, if you want to build a digital twin, in this case, you will need a module that will perform modeling. So starting from real data and, for example, knowledge about potential attacks, you will build a model of your system that you also feed with real-time information from the real context. Then you will need an engine to run one or more digital twin instances. And finally, you can either allow an external module to interact with the digital twin engine, for example, to performing operations, so to simulating actions on the real twin, or you can introduce a prediction module that runs the digital twin and analyzes the data and performs predictions for the future. For example, you can build a digital twin using a network emulator like the one that we developed with the University of Dresden, because this is a software that using SDN and NFV enables to have a very flexible and programmable replica of a packet switching network, while still maintaining the capability to analyze real-time traffic, even if this traffic is predicted, but we can generate real traffic, we can analyze at the packet level, at the bit level, what is happening. And in this way, we can have a very sort of flexible software that we can transform into the twin of our real networks. One of the big problems in these cases is how to synchronize the physical and the digital twin, because in here there is quite a complex picture, but the concept here is that if you look from the top, what you need to have is a communication between the physical and the digital twin. So you will need some time that I call T-collect for collecting the data. For example, you analyze the traffic for 2 minutes. Then you need to analyze the traffic and to transfer it to the digital twin, so that the digital twin can either play back, but it will play back this trace with quite a long delay that is called T-sync here, the synchronization time, or it can, if we also want to run the prediction, so to look in the future, this will happen also a little bit later. The concept here is that, of course, you cannot zero those delays, because there is time for acquiring the data, time for transferring the data, and so on. But for synchronizing and run the digital twin in a real-time manner, predictions are very important, because they allow you to somehow go back in time, so to reduce the delay by introducing a prediction delay. So as far as I can look in the future, this time can be used to reduce the delay, because I can start playing back directly the digital twin in the future that I predict. And this allows me to reduce the playback delay. So it allows me to have a digital twin that in real times allows me to look as much in the future as possible. However, there is always the problem that my predictions can be wrong. So I need also a way to maintaining stable predictions. And for example, we made some experiments using a simple proportional integrative derivative controller that provides feedback. So every time you receive new data from the physical twin, the digital twin fixes the predictions so that it can resynchronize as accurately as possible with the physical version. Just to explain you what it means, let's look at these two diagrams. On the left, you have how much you look back in time. So 60 seconds, 3 minutes, or 6 or 5 minutes, sorry. And of course, typically, the more you look in the past, the better is the information that you can predict, because you know better how the system works. On the other side, you want to predict the future. So you want to look forward, maybe 300 seconds or 600 seconds that you see on the right. And in this case, of course, the longer you look in the future, the more errors you can do, because the system might change. So the idea of introducing the feedback with the PID controller every time you get new data from the real system is to reduce the error that, as you can see here, just in 10 seconds, for example, if you do some simple predictions, this error can be halved, for example, from the orange to the blue, just by introducing this feedback loop that allows to just rebring, let's say, the prediction back to the real data. And this is important because you don't want, of course, your prediction to diverge, but you still need a continuous and periodical link from the physical to the digital twin. So let me show you now another kind of issue that where the digital twin can be useful. And this is energy efficiency and, let's say, MEC, so mobile edge cloud, because this is a problem that probably will emerge quite strongly in the near future, since a lot of use cases predict that mobile edge will become a pervasive technology. But mobile edge, so to bring computational power to the edge of the network, is also constrained by the fact that you need to be very pervasive. You need dedicated hardware to increase your computational power. You will have a very extremely variable load, because the idea is that you track basically the users or the end systems, and you move your tasks or your service containers as near as possible to the end users. So it's difficult to have a general model, and at the same time, it will be a scenario where power availability will be probably scarce, because you need to bring more power to the edge. Maybe you want to use renewables. So it's a challenging scenario because of high heterogeneity, because you don't know exactly the impact of virtualization in the power consumption, because power consumption is related to hardware at the end. But there are a lot of overhead layers that happen in TCP/IP, but also virtualization. So we wanted to understand how we can optimize a mobile edge system. And in this case, we built a digital twin of the 5G network, in this case, supporting the edge. So this is just a conceptual diagram to show you how we emulated the RAN on the left, the MEC node in the middle, and the cloud on the left, deploying a real 5G software in an emulator. Here, in these cases, we use the concept of digital twin by replicating both the limitations of the hardware, and this is done by limiting the amount of resources that we give to each of the components of the system. Here there is a diagram, for example, if we want a Docker container to behave in a similar way as a Raspberry Pi embedded PC. So we wanted to constrain the computational power of each of the parts of the network in order to represent the real system. This allows us to study already to find some trade-offs. For example, here you see a diagram that shows you on the left the trade-off between the throughput and the CPU load of the Mac node. And depending on the amount of computational power that you associate with the Mac node, you see they have different colors and different behaviors. So basically, this is not yet related to energy, but it shows you that you have limitations in the combination between computational and networking capabilities that you can put in the system. And this we measured in the emulator. So this made sure that we could constrain computational power of each of the components. We did it by limiting the power associated to each Docker container that we used in this system. However, the interesting part is how we modeled energy consumption. And what we did at the beginning was to build a static version of the digital twin, which basically we built by performing real measurements on a testbed. So we used simple power consumption measurement devices that are plugs that we attached to all our devices. And we generated different workloads in terms of CPU power and communication power required. And what we find out was that depending on the different virtualization strategy, bare metal containers or virtual machines, the response of the system in terms of power consumption and performance is different. Here you can see the three cases in terms of data rate versus CPU power versus consumed power. So the idea of this, that you can also build runtime. This is an example of building the same figures, but acquiring the data in real time. By using this digital twin, you can, for example, improve your capability to optimize power consumption. Because, for example, if you simply use the digital twin for what-if scenarios, so to analyze different solutions, you can still get quite good results, as you can show, as we show in this example, where we use the digital twin information. So in this case, the digital twin for us is only this 3D surface. So it's only the surface that we measured for each of our hardware devices. And we use this to define the best position of functionalities between the cloud and the edge. And here we compare the optimal, that is the blue line in terms of power consumption, with two other solutions. One is fully random, so just assigning randomly the services, positioning them randomly, and the simplest possible approach, but with the digital twin, which is to still make random assignments, but to accept only those assignments that the digital twin accepts that don't violate QoS constraints. So we use the digital twin to check if that setup can satisfy the QoS of the system. And you can see already that even though we don't make the system much more complex, we just delete some potential solutions, you see in the diagram that is labeled B that we reduce by half, roughly, or at least more than 40%, the consumed power, maintaining also quite, it's the green line on the top, basically the optimal solution most of the times, without violating only once, in this example, the QoS of the system. So this shows you that simply by having more awareness that is enabled by digital twins, we can improve the system behavior and make it flexible, because now whatever hardware I use, in a small amount of time, my system is capable of replicating its capabilities, its response surface, if you want, and use that for taking decisions. Another important application is at the physical layer, because I can use digital twins also to operate in perspective of evaluating the coverage areas. So here, while I explain you, I'm playing back just a conceptual example. A typical application of digital twins is to build a coverage map. In this case, you see an area near to the university. So to build a 3D, very high definition replica that provides an estimate of the coverage areas provided by a 5G base station. We did some experiments on this, and this is how we built, in this case, the digital twin. So we started from 3D maps that are openly available, for example, from OpenStreetMaps. We integrated it in a 3D modeling and rendering module. In this case, we use Blender, but you can use any 3D engine. And then we used a library for ray tracing. In the example that I will show you, we use Sionna library from NVIDIA that is for GPU processing, with the idea to build a first approximation of the coverage area. However, this is not a digital twin if we do it like this, because we don't use any real, let's say, information about the 5G coverage. We only build a simulator. How we integrate the digital twin concept here is that we used a software, in this case, a very simple one, it's called NetMonster, that allows to monitor mobile network connections. So what we did is we started from a preliminary version of the coverage that is simulated, and then we integrated, in order to build a digital twin, real data in the system to fix and provide a better prediction of the coverage area. So at the beginning, we started with an area. This is Trento. We built the 3D version, and we used the ray tracing module in order to compute a coverage area. In this case, there is the base station is the red dot. Then we made actual measurements. Here it shows you where we made the measurements are the dots that you see on the right side with respect to the coverage area of the base station, that is the red square point. And on the left, you see the distribution of the measurements. So basically, the Sionna simulator is fairly good, even though there are some outliers. So here you see in green the interval of plus and minus 10 dB, and you see the red as the ideal curve. So then, starting from this, we integrated some real measurements. Here you see some squares about the areas that were affected by the errors, or they are improved. And in this case, we simply tried to mitigate the errors using a Gaussian distribution with different parameters to check how to propagate in the neighboring pixels the information that is collected from the actual physical, let's say, and real propagation that we measured. So finally, what is the application of this? For example, we could study the communication between the drone and the base station. Here there is an example that shows you a little bit the ray tracing. So we can study and emulate what would happen if we want to use a drone, for example, in an area, to check if the communication is stable, if there are problems, or if there are any uncovered areas, for example. But more interesting for us is, for example, to study how we could improve 5G coverage by introducing temporarily some drones. Here you see two simulations introducing drones with omnidirectional antennas on the left, and using drones with directional antennas on the right. And you see that, of course, the coverage areas differ, but what is interesting is that they provide a fairly good and accurate version of the real measurements, because in some points those are aligned exactly with the real measurements. But for example, we don't need to run a drone extensively in the whole area, because we can interpolate the missing values using the ray tracing module. So this is, I think, a very interesting application that helps planning the network, or helps planning, for example, temporary hotspots where you can send some drones to provide increased signal to noise ratio, or to cover uncovered areas when there are traffic hotspots. Then finally, before closing, I wanted to show you another example. This is the different kind of digital twin. It's not exactly a network digital twin, but it's a digital twin used for, let's say, networking application to augment the data sets. For example, here you can see, I don't know if you're familiar with this existing data set. Several years ago in Stanford, they recorded this footage from a drone. You can see it on the right side. It's an actual footage. And in the left side, we rebuilt in 3D a similar scene. And what we can do is, by analyzing the real video, we can build the same trajectory of people and replicate it in the synthetic scene, so that we can replicate the real video. And for example, as you see now, it's I put some of the real people in the synthetic scene to populate the situation, but I can also add and augment the data set, because maybe I would like to understand what happens if there are more people. So I need to build digital twins of people, and we did it with some behavioral models. And here you can see we can add as many as we want. For example, here we have 100 people more, and then we can build data sets for training, for example, AI, because we don't only use these from this perspective, but we can modify and emulate, for example, a drone flying by and analyzing the situation, as you can see, for example, from different viewpoints. This is an example of, as you can see, movement is quite realistic. It's an example of how you can build a data set starting from real data, but to augment it, for example, for the purpose of building new data sets for AI and machine learning in situations that are maybe difficult to replicate in reality. Finally, some people already is thinking of building networks of digital twins. So not to have one digital twin only, but like in the previous case, if you assume each human is represented as a digital twin, to link several digital twins together. So this is surely an interesting perspective for the near future. And some people is already speaking about the Internet of Digital Twins as a sort of implementation of the metaverse, where there will be let's say the benefits will come from the interaction of the digital twins. That is something that at the moment I couldn't show you here, but it will be a subject for some future work on the topic. So a few more things before I close and open for questions. One thing is we asked ourselves who should develop digital twins or network digital twins, because some people might say, okay, you can build the digital twin as an open source asset, like we are doing in my lab. And in this case, it's the community that builds digital twins. So the community builds software that is open to everyone to replicate the existing network counterparts. But there is also another interesting scenario for digital twins, because no one tells you that the digital twin must be a white box. So it must be something that you can look inside. For example, another interesting perspective could be that the vendors of actual physical objects like a base station or a switch or a router, they can give you also the digital twin, but as a black box, so they don't need to disclose the internal functioning of their system, but they can give you a, let's say, precise replica of their behavior, because maybe they can protect privacy or patented information, but still allow to perform experiments, for example, to run what-if scenarios and optimization. So the digital twin can be also a tool that can help in privacy preserving or let's say obfuscating some of the functionalities, because the target is to have a sort of input-output reliable functioning, not to be exactly the same as the physical system. So the idea is to replicate the behavior, but not maybe the implementation. So moving forward, at the moment, research is going towards integrating digital twins for networks, for sure, in 6G. There are already some white papers from SNSJU and ETSI that predict the presence of digital twins of networks inside the network automation loop. And in general, what can we use the digital twin for? We can use them for training AI and machine learning. So the digital twin can be a way to generate a data set, as I told you at the end of this presentation, but you can use it also for performing modeling and prediction of real systems. And then there is this issue of black box versus white box. So should a digital twin be completely open and sort of transparent, or is it in other cases better to have a black box, so a reliable input-output relationship, but that is obscured, so it does not need to be disclosed? Both can be integrated, of course. This will depend probably on the importance or let's say the marketing of the different kind of digital twins. Finally, some people would say, okay, it's something new, so what about standardization? So is it already a mature technology, or is it something that is coming out of the blue? So here I try to collect a few things. As I mentioned before, ETSI is working on digital twins within the ENI working group. If you want, here there is the link. There are already a few white papers that include network digital twins. So this will be for sure an item that will be addressed by this working group. Another relevant working group is the zero-touch service management. And in this framework, we are currently preparing a proof of concept with other companies to show to this working group in order to show the potential of digital twins, but also in the IRTF, there is a recommendation being discussed that is a draft that is called Digital Twin Network Concept and Reference Architecture that you can see on the right side. So I think that the position of the digital twin and its interfaces are already starting to be standardized. So this is a technology that probably can mature extremely fast. So to finish the presentation today, I think that at least I tried to provide you some reasoning about digital twinning can represent good solutions for networking, and in particular, they can be useful modules to add to 5G and 6G architectures. As I showed you, there are promising results, even though there are still several open challenges in the field. So I believe it's a good topic, not only for research and academia, so it's not only a theoretical work, but as I presented you, standardization is already moving quite fast around digital twins, so that it is already becoming sort of nearly mature technology. And for this reason, it would be also interesting both in standardization to be finalized and to be integrated in, for example, the upcoming 6G standard, but also for companies that are operating in the sector. This concludes my presentation. So I think I stayed in the time as agreed, and I'm available for questions.
Perfect. Very interesting. Thank you, Fabrizio. It was a very interesting and detailed topic tutorial.